we have a computer vision system that identifies key goals in the course, along with a high-level planning module and a local laser scan mapper node. We also have a rapidly exploring random tree planner and an RRT star node for increased path optimality. Finally, we have a low-level path follower node that is able to execute the intentions of the higher-level modules.
Here's a way we use approach marker detection. First, we record the video of the marker under different brightness. Next, we extract the pixels colors and store them into the files. While the car is running, it keeps checking whether there is any marker by looking up the files. After finding the marker's position in the video, we can calculate the coordinate in the real world by giving the p-tracks and height and width of the marker's image. Finally, we pass the position information to RRT so that it can plan the route toward the marker.
In our implementation, we focused on giving the robot a strong ability to plan at all levels, and the top-level planner is the keystone which enables this. Given the location of the robot, the relative location of markers, and a predefined path around the course, the high-level planner picks feasible local goals to make progress along the path or drive over a marker. The local mapper is a support structure for the local planner. It takes the laser scan input and projects it into a local grid aligned with the global map and centered on the car for efficient overlay. In this example, the dark green shows the predefined path, and the light green shows the actual robot path produced by the local planner to achieve the goal produced by the top-level planner further ahead on the path. All this is shown in context with the global map and the local map overlaid.
We use a rapidly exploring random tree to plan trajectories between where we are and where we want to be. This samples points in tree space and connects them with circular arcs to the path we've already explored. The green line shows the path that gets closest to our goal point. If we detect an obstacle during planning, we prune the parts of the tree which are now invalid due to that obstacle, which then causes us to replan around. We can do this multiple times and we'll see it cut out various sections of the path. RRTs make no guarantee about optimality, as you can see by the indirectness and curvature of this path, which is why we considered using an RRT star algorithm.
Here we have RRT star running repeatedly so that you can see the types of paths that it finds. Generally, they are pretty short and pretty straight, but because of the nature of randomness, sometimes the paths created are longer and curve around obstacles you don't need to. However, it appears to be generally working, and most of the paths it finds are fairly optimal or close to optimal.
In spite of our robot's high-level planning capabilities, we still need a reactive controller to execute the planned paths. Our path follower node does this while also intelligently compensating for latency upstream and robot pose uncertainty stemming from localization error. Our path follower node also tries to minimize error by automatically slowing down on corners